Dear students, in this module we will understand the basic concepts of crystal field theory. In particular, we will try to understand what is crystal field stabilization energy, and in this module we will try to understand following points. First one is what is the crystal field stabilization energy. Second point which we are going to understand how we can calculate crystal field stabilization energy. The third point which we are going to understand is stability of various electronic configurations, and then we will also try to see how to evaluate the crystal field stabilization energy. Now let us first try to understand what is the crystal field stabilization and how the this energy can come into the picture. Let us say we take a metal ion, some M plus ion in the gas phase. In this case, whatever the orbitals which are present inside the metal ion, these orbitals are going to be degenerate. That means if we take this metal ion as a transition metal ion, let us say with D3 electronic configuration, when we say degenerate, all these orbitals are going to be at the same energy. That means if this is what is the energy scale, all these 5d orbitals are going to be at the same energy state. Now this is the situation when we say the gas phase. Now if the same metal ion is under the influence in a, say, condensed phase, or we can say in the solution phase. In that case, what will happen? We can look into in a better understanding that the same metal ion, say M plus ion, is being influenced by variety of solvent molecules. For the understanding purpose, we can say these are the ligand which are, for example, approaching from all possible direction. That means if we take the coordinate, we can say this is the x-axis, this is the y-axis, and the third one is z-axis. That means the ligands or the solvent molecules, they are approaching the metal ion from all three directions. So what happens when this type of situation arises? The d orbitals which are inherently present in a metal ion, they do not remain degenerate, they get influenced by the approach of this ligand which are approaching the metal ion. Now we will try to look into this concept more clearly. Say a metal ion which is being approached by different ligand L. Now there are several possibilities. What are those possibilities? That when these ligand L approach the metal ion, they can create a octahedral ligand field around the metal ion. That means what is the octahedra? Whenever there is a basal plane, the 4 ligands are approaching from the basal plane, and then 2 ligands are approaching from the axial position. So these are basal plane when the ligands are approaching in the x and y plane, and these are the axial position. But what is important is all 6 ligands are identical, as well as they are in identical distance apart from the metal ion. So in that case, what will happen? The earlier 5d orbitals which were degenerate in gas phase, because of the approach of these ligands from a different direction, that means x-axis, y-axis and z-axis, they will actually split into 2 set of orbital, and if this is the barycenter, then they will split three sets which are lower than the barycenter and 2 sets which are above the barycenter. In fact, we can say this is what happens when there is energy. So that means these 3 orbitals which are lower in energy, in fact these are stabilized. These set of orbitals are called T2g orbitals, and the 2 orbitals or 2 set of orbitals which are above the barycenter, these are higher in energy, these are called EG orbitals. Now what will happen? This is the situation which is in the condensed phase or in the solution state. That means when the metal ion is no longer in the gas phase, that means it is under the influence from various ligands which are approaching the metal ion from all 3 possible directions. So this splitting of orbital is unique whenever the ligand approach the metal ion, and the gap between this set of orbital is called delta, as we are talking about octahedral. So this is basically del O, which is nothing but the octahedral, and this particular gap is called crystal field stabilization energy. So this gap between 2 sets of orbital is called crystal field stabilization energy. So let us revisit that point. So we have 2 sets of orbital. Remember, these orbitals are exactly, they go up and down. The one which go up are called EG set of orbitals. The one which go down are called TG set of orbitals. Now this gap, as I have just explained, this gap is the crystal field stabilization energy, and we can actually calculate this energy. That depends how many electrons are present in the lower set of orbitals compared to how many electrons which are present in the upper set of orbitals. Remember, they differ by the energy. So this can be explained as minus 0.4 x plus 0.6 y and the octahedral splitting, where x is number of electrons in T2g orbitals and y is number of electrons in EG set of orbitals. We'll take few examples about crystal field stabilization energy. Let us start with a D1 ion. We can take this example as say titanium 3 plus ion which will have D1 electronic configuration. So remember, we are discussing in octahedral ligand field. We can take 6 ligand, for example titanium 3 plus ion, which is surrounded by 6 water molecule. So that means we can schematically draw, this is the basal plane, 4 water molecules are present in the basal plane, and then 2 water molecules are occupying the axial positions. Now for this ion, remember it's a 3 plus, so that means it's a D1 electronic configuration. So for this one, again we will have distribution of orbitals and subsequently distribution of electrons in T2G versus EG set of orbitals. As we have only D1 electronic configuration, the one electron will occupy one of the orbital T2G set of orbital. Remember, all these 3 orbitals are degenerate, so it does not matter whether the electron goes to the first one, the second one, or the third one. Now when we go to the second example, say a D2 ion, in that case what will happen to the filling up of the electrons? So this is the T2G set of orbital, EG set of orbital. So the first electron will go to the first one, the second one will go to the second one. As we have only 2 electrons, so these 2 will occupy any of the set of orbitals which are available under the T2G. We can move further. We can take a metal ion with D3 electronic configuration. Will have the same situation, the degenerate set of T2G orbitals and degenerate set of EG orbitals. As we have 3 electrons, so there is no problem. All these 3 electrons will go and occupy T2G set of orbitals. Remember, this is the energy scale, so we have to start filling up the electrons from the lower energy or the electronic configuration which is more stable. So up to D3 situation or up to the metal ion with D3 electronic configuration, there is no confusion. Now when we go to the fourth one, that means the metal ion with D4 electronic configuration, or we can simply say a D4 metal ion. Now you will see that we will have 2 different type of situations. For example, we can call it 4A. So let us try to fill up the electron, the first one, the second one, the third one. Now what will happen to the fourth one? Okay, maybe in the 4A, the fourth one goes to the top, but then we have a alternate situation. Let us call it 4B. So in 4B, so the first electron, the second electron, the third electron, but rather than going to the EG set of orbital, let us say the fourth electron goes to the T2G set of orbital. So which one is favorable? Which one is allowed? For your information, both these situations are allowed, but what actually depends is how much is the gap between these two set of orbital. And remember, that is what is our crystal field stabilization for an octahedral ligand field. That means if this gap is very large, this fourth electron will have no option but to go to the T2G set of orbital. For some reason, if the gap is less, then what will happen? This electron, rather than going to the T2G set of orbital, it can always go and occupy the EG set of orbital. So this situation leads to two different combinations or electronic configuration. The first one is called high spin electronic configuration, and the second one is called low spin electronic configuration. So now we will try to calculate the actual number for the CFSE. So remember, I told you that CFSE can be calculated as minus 0.4 x plus 0.6 y and then crystal field stabilization gap. Remember, the x is number of electrons in T2G set of orbitals, and y is number of electrons in EG set of orbital. So let us say what will happen if we start from a D1 electronic configuration. So we will try to see where exactly the electrons are going. So with one electronic configuration, there is no problem. The electron can go to any of the T2G set of orbital. So what is going to be the CFSE for this combination? CFSE is going to be minus 0.4, x is going to be 1, so multiplied by 1, plus 0.6, as there are no electrons, y electrons, so this is going to be 0. So that means CFSE for the D1 electronic configuration is going to be 0.4. Now let us take an example of D4 electronic configuration. So what will happen? We'll have the same T2G and EG set of orbital. So this is the first one, the second one, the third one. Let us say we take the first example as the high spin. So the fourth electron goes to the EG set of orbital. So what will happen to the CFSE? CFSE is going to be minus 0.4. Then we have 3 electrons in the T2G set of orbital, so multiplied by 3 plus 0.6 multiplied by 1 electron which goes to the EG set of orbital. So what will happen? This will be minus 1.2 plus 0.6. Effectively it is going to be minus 0.6 for the D4 electronic configuration. Okay, what will happen if we take a D5 high spin electronic configuration? Let us fill up the orbitals. So the first one goes to the T2G set of orbital, the second one, third one, fourth one, and the fifth one. So how the CFSE is going to change? So we have 3 electrons in T2G set of orbital, so minus 0.4 multiplied by 3 plus we have 2 electrons in EG set of orbital, so 0.6 into 2, and we see the CFSE is 0. What is the meaning of that? Any metal ion which has D5 electronic configuration is going to be very similar to that of D0 electronic configuration. Let us take one example to understand whether we are right about our calculation of crystal field stabilization energy. So the example which we can take is the exothermic enthalpy calculation. So for this particular example, we can take metal in 2 plus oxidation state, that means 2 plus metal ion for the first transition series. So that means we start from a metal ion which is in M2 plus state. We start from the gas phase, and this gas phase metal ion react with 6 water molecule. That means this is going to be in the liquid state or the condensed phase, and then it will form this complex. That means a metal ion in 2 plus state is surrounded by 6 water molecule. And what we are trying to understand, how much energy is being generated or being produced in this particular step. So this is basically we are looking into what will happen when the ligands, which are water molecule, coordinate a metal ion in the gas phase and produce this metal aqueous species. And this energy should actually correlate with respect to energy which is being observed from the experimental data. Okay, so we are trying to look into enthalpy for the hydration for first transition series of metal ion. So what will happen if this is the metal ion, remember in +2 state, and we are moving along the in this fashion, that means the transition series starting from the scandium, titanium, vanadium, chromium, manganese, Fe, iron, cobalt, nickel, copper and zinc, and all these metal ion are in +2 state. So when we go along this side, what happened to the size, ionic size of the metal ion? The ionic size actually increases. That means if these metal ion form a bond with 6 water molecule to form a species of this type, when we move from scandium, titanium to all the way to zinc, the enthalpy should actually increase more and more as we move more and more towards the right side of the series. That means let us try to plot whatever I have just said, the enthalpy with respect to M 2 plus metal ion on this side. We can always start, we can make them on the x-axis. That means the 0 point can be taken as calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So on the x-axis we have M +2 ion in the +2 state, and on the y-axis we have delta H, which is nothing but the enthalpy for the hydration of M2 plus ion. So if we are correct in our thinking, we should actually expect a straight line. But we don't actually expect the straight line. We actually see rather than seeing a straight line, we see this type of profile where some of the elements, for example calcium, is exactly at the expected place, manganese is again exactly at the expected place, zinc is also at the expected place, but then rest of the metal ion, they do not fall on this straight line, they actually fall on this type of humped surface. The same is true after the metal ion manganese, for example iron, cobalt, nickel and copper. That means something is different for the calcium, for the manganese and for the zinc. Now let us try to see what is different for these three metal ion. So if you write the electronic configuration of calcium, you will see it has no d electron. That means the d electron count is 0. What happens if we take a manganese? Remember, we are taking the example for high spin state because we are taking a very weak field ligand water molecule. So manganese 2 plus, the electronic configuration is going to be d5. Remember what is the d crystal field stabilization energy for d5 ion? We have just calculated, it is 0. What is going to be the crystal field stabilization energy for the calcium 2 plus ion? The CFSE is again going to be 0. The last one is zinc 2 plus ion, which is a D10 metal ion. The crystal field stabilization energy for this ion is again 0. That means whether a metal ion has D0 electronic configuration, D5 electronic configuration in high spin or D10 electronic configuration in any of the spin, we will always have 0 crystal field stabilization energy. But then what happens to the other metal ion? Remember, these are the metal ion, for example scandium with D1 electronic configuration, titanium with D2 electronic configuration, vanadium with D3 electronic configuration, similarly chromium with D4 and so on. We will have only 2 deviations starting from the D0. The first deviation will come for the manganese, where the electronic configuration is D5, which will lead to 0 CFSE, and the next one is going to be the zinc, for which CFSE is again 0. For all these, for example scandium, titanium, vanadium, chromium, iron, cobalt, nickel and copper, the CFSE is not 0. What is the meaning? That this deviation from the linear line is because there is a sizable amount of CFSE which is causing difference in the value of enthalpy for the hydration of metal in +2 ion. So this is a very good example to understand the importance as well as the significance of crystal field stabilization energy for various transition metal ions.